Welcome to this video lecture on technology and innovation management. This video is part of a three-part lecture series about technology and innovation management on the topic of digital technology and digital technology management in the firm. In this lecture here, we will be talking about what is different about digital technologies. We have said before, and this is not part of this lecture, but what we want to look at is how technologies themselves have changed since what is called the advent of the digital age. So an accumulation of phenomena that all occurred in between roughly 2007 and 2020. So over the last 15 or so years, it is now 2023, where we've seen a number of phenomena that are all connected to one another, that all together characterize what is called this advent of the digital age. So number one, the rise of personal mobile, fully capable computing devices. So the ubiquity of mobile computing that allow people anytime, anywhere, anyone to really leverage digital information and communication technology and internet. Second, the rise of social networking platforms and the connectivity between not just millions, but really billions of people on the planet. Third, the rise of digital connected devices and objects that have overtaken the humans in terms of population, leading to a term that has been coined the Internet of Things, characterizing that the internet itself is not actually primarily a place where humans exchange information, but has a long time become an infrastructure for things and objects to communicate and address and talk to another. Fourth, the rise of investments and developments in artificial intelligence and the capabilities of computing devices and connected objects to become smarter, so to speak. So to carry out more and more operations in an increasingly autonomous fashion. And fifth, with that, an exponential data growth, because all these technology-infused, enabled, or embodied activities both generate and operate on digital trace data, so evidence of activities and events that occur online, click streams, content, cookies, and all these things. Together, these five factors characterize this notion of the digital age and the basis for the changes in technology that this lecture is about. So to start off with, a very simple way to think about this is what is different in technology in the firm is that they're no longer just a piece of software in a computer in a back office room of a company, but they're front and center in, for example, the products themselves, right? If you look at the right-hand side, which shows a wearable device, a Fitbit, a fitness tracker that contains technology in the product, or on the left-hand side, a digital autonomously driving car that runs on digital technology itself. Whereas beforehand, before this digital age, most technology in the firm actually looked like this: a piece of software, in this case, a customer business planning module from the SAP enterprise system, where we had software such as an Excel table, an Oracle database, Microsoft Word, or in fact SAP and similar pieces of software that would actually be shielded away from the product and very often the customer interface, and were supporting the back-end operations and were living literally on computer screens. And conversely, what we have seen since the digital age is the actual conversion of the offerings and products. So one example to illustrate that is when you think about music media, like a cassette, later an LP or a CD, and then what later became an MP3 file or a streaming service. Yeah, so old people like me would still remember this connotation here, that you could actually rewind and forward a cassette tape with a pencil. And this product, this offering that that firms developed and sold to create and capture value, has of course changed into these digital objects. Yeah, whether it be Apple Music, a Pandora streaming service, which was basically a first type of Genius / music recommendation streaming service, or of course, like a modern day equivalent such as Spotify, where no one actually still has or buys or even produces tapes as a music product, but instead we all access and stream music directly into our speakers, our headphones, or wherever else. So what is different here? One of the key difference in digital age technology as opposed to information technology or other types of technologies that were either in products or, more importantly, in the operations of a firm that enabled the value chain of a firm is this notion of digitization, which is a necessary but insufficient condition for all the changes that we see now. So digitization means the encoding of analog information into a digital format, namely this language, which are called bit strings, which are a series of zeros and ones. An example is given here, and where you have a bit index where every bit literally can only be a 0 or 1, and speaking in terms of engineering aspects, this would be literally electric current is flowing, 1, or it's not flowing, right? So it's like sort of switch on, switch off, and then you can construct along sequences of these bit strings to encode all sorts of information. So for example, this number here, 01100 and so forth, could be a number, it could be a letter, it could also be information relevant to a piece of art. So it could be like a pixel position on the screen, it could be a color, it could be anything else, it could be a piece of sound, whatever else. Now, what is important here is that this digital format, these bit strings, have some very unique characteristics. You can think of it as a language, but there's something peculiar about this language. So first of all, it's a communicable language. Bit strings is a language that literally any computer can speak, as long as it's a standardized interface, as long as literally this current and the sequences arrive in zeros and ones. Any computing device that is operating on a von Neumann architecture, which are all electronic computers these days, can access, understand, and process this language. Yeah, so it's like a truly universal language that literally every computer speaks. A second, it's editable because it's a non-material language, because current is flowing or not. It also allows us, of course, to change these sequences of zeros and ones, which means digital formats, digital bit strings can be reprogrammed. We can change whatever they're saying. And the third aspect that is mentioned here is layered. I'll talk about this in a little bit about what that allows you to do, because the information that is relevant here and that we express in a digital format is not tightly coupled, is not tied to a particular bearer of a piece of information. So for example, here you can think of this screen here as a piece of paper, a printout, where whatever it is on the printout, I would have to, I could actually, it's stable and it can't be separated. But because this PowerPoint slide deck itself is a digital technology, I can actually literally go into it right now as we speak, go to the correct slide and make changes here. So for example, there should be a full stop here and here. And now the information is changed because I can separate it from the bearer. And it's editable. And a fourth aspect here is that this particular language, the digital language, is syntactic, but it's not semantic. What that means is that it has very clear grammatical rules that can only be zeros and ones, and they have to be in this bit index that is of particular length, 18, 16, 24, 32 bits. But what these sequences of zeros and ones stand for is freely definable. So as I said, this sequence above here could be a number, it could be a letter, it could be an image, it could be a piece of sound, it could stand for anything. A nice example of what this language now allows you to do, if you take any piece of offering that you have, such as a boarding pass that would be issued by an airline, we see how that changes the very product itself. On the left-hand side, you see a classical boarding pass, which was a piece of paper that had important information for processing your process through the airport, with key information, your flight number, your seat, your gate, your destination, your name, stuff like this. Now, we all know that this information and the processing of this information, your sequence of steps through the airport can change. The airport might be late, it might land on a different gate, you could be reassigned a seat. The arrival time could be different, etc. Previously, when that happened, you literally had to go and get a new boarding pass. There would be a desk somewhere with a person who would literally print you a new boarding pass with the updated information. Now, as airlines started to convert this classical boarding pass into a digital format, they converted it into a digital product, and they could now leverage these key characteristics that I just explained. So first of all, it's now communicable. So now it doesn't matter whether you open your boarding pass on your laptop, your tablet, your smartphone, your iPhone, your Android phone, or even your printer on a piece of paper. All of these devices can access the same information because they all speak bit strings, so to speak. Second, all of this is editable. That means if any of the relevant information for processing your sequence of steps or re-airport changes, it can just be updated on your device. So in other words, if your seat number changes, it would literally just send this information to your smartphone. You wouldn't even realize. If your boarding time changes, it would realize that. It could send you a notification faster than you could see it at a display screen in the airport or hear the announcement. So that is what is interesting in this new type of technology, the digital technologies, to the firms, because it literally changed their products and in this sense made them better. They're more convenient for users. They are also more efficient for the organization, because now that everyone has a digital boarding pass, first of all, you don't need to print anything anymore. You also don't need to have a desk with an employee whose job it is to send people updated boarding passes as soon as the information changes. Now we can literally make do without any of these other resources, which is faster, more convenient, but also cheaper for organization. So this digitized boarding pass is communicable. It's also layered. It's independent, all the relevant information, and decoupled from the bearer. So it doesn't matter whether you open it on your device, on your laptop, or at some other computing device, because the information is decoupled from the display of it, and it's editable. I explained all of this. So on basis of this necessary but not sufficient digitization and the changes through this bitstring language, we now have digital capabilities that provide new capabilities that are different and emergent, and so different from those that technologies had in the past, that are now creating all these changes in the role of technologies to the firms, and are part of the reason why, for example, they no longer just exist on the computer screen and back office, but found their way into the products and offerings and customer interactions of a firm themselves. The 5 key capabilities are listed here: modularity, addressability, agency, reprogrammability, and datafication. And in what follows, I will explain all of them. So first, I'll start off with giving the colloquial explanations for these 5, notably academic terms that describe them. So with modularity, we mean that we can assemble different components, say, of a product on different layers, and keep these separate and or remix them between different products and different offerings in different constellations. So modularity is a key principle that allows us to take one product, say, and disassemble it, decompose it into individual modules that can then be rearranged either in design or in use. Addressability means that technologies or products in which we have these technologies can refer to themselves, they can talk to themselves, they can talk to other objects that have the same sort of technological capabilities. Everything is addressable, and so if you want the metaphor, you can call them, or they can call it themselves or each other. A third capability that is emerging is here the notion of agency. Agency means the ability of something to do something on their own. This, again, let me edit this slide as we're talking, because I can. This should, of course, be own, not one. There you go, right? So even for me, I can make use of these capabilities as we speak. So agency is the capability of an object or an agent, an actor, to do some things on their own. And the key thing is that, of course, humans always have agency. We can do things. But increasingly, also technologies or even products can do things on their own. A simple example of that would be a phone giving you a push notification. Reprogrammability, this stems from the editability of bitstring technology, means that things can be changed, they can evolve, they can be updated, they can become different over time. And finally, datafication means that everything that has digital technology in it consumes and generates digital traces. It leaves footprints when used, and this data then datafies everything it does, and itself becomes a source of information that firms or others can tap into. So in what follows, we will go through these different components. You can stop and pause at any time, of course, and then continue watching later. So the first aspect, the first capability is this notion of modularity. Modularity is achieved in technology through homogenization and decoupling. Homogenization describes that because all digital information assumes the same form, namely this language of bit streams, it can be processed in principle by other types of technology. All digital technology is homogeneous in this sense. It's uniform. What that allows is, that means that if I am able to take different components of anything, of any product, for example, and create an interface that allows information to flow in and out of these different modules, these different components, then I can remove any couplings that might exist. So any two things might have to be tightly coupled, but I can keep them separate and just communicatable. And that is possible because I can, they all speak the same language. So as long as I find a way to, for a module to leave out important information, as you produce important information, another one to actually access this information through what's called an interface, then I can keep all these things separate and loosely couple them. Yeah. So a counter example is, for example, what's called a tightly integrated product, such as a high-precision Swiss watch. A Swiss watch is a product that has multiple different components. Yeah, so it has the dial, for example, it has an armband, it has all sorts of mechanics inside it, but they're tightly integrated, they're tightly coupled. Yeah, you can't just, take one out and replace it with something else. As soon as you take one component out, the entire thing won't work anymore. And this tight integration in certain types of products was a key architectural decisions for firms, because it allows you to optimize the entire thing. So it's a high precision watch because it's a tightly integrated product. But of course, most products are not of this high precision, high-end market. For most products, we have seen the rise of what are called modular architectures. Yeah, IKEA is a prime example of a modular product architecture where you have products such as, furniture and beds and sofas and whatever, that are actually composed of multiple fairly independent components that you can put together, or in fact rearrange and recombine and reconfigure as you see fit. On the left-hand side, you see the same for a bicycle, where you have a bicycle frame, you have a saddle, you have brakes and wheels, transmission systems, forks, and all of this, they can reconfigure them into the bike that you want. And even all the components could be potentially even be produced by different firms, as long as you agree on standardized interfaces. And this is really the key, right? So for example, in the bike example, we do have companies such as Shimano, and they focus, I believe, on brakes and transmission systems. And we have other companies such as, I don't even know, Canyon, for example, which are making the frames. And they do have agreements in place that the frame component has a standardized interface that would fit the Shimano gears and brakes and transmission systems. So to have a modular architecture, this notion of interface between the different modular components is really, really important. And in traditional products, we would have to have agreements in place, maybe standards in place that would, make sure that we have, interfaces between these modules. Digital technology now makes this a lot easier and simpler, because digital technology not only has a modular, but also a layered architecture, a layered modular architecture. The key components are typically content, service, network, and device. For example, your iPhone is a device. It runs either on wireless LAN or on a 5G network, which is the network layer. On top of that, it yields certain services such as the App Store that allows you to download new apps, and the apps themselves provide content. All of these are modules in their own right, and they're layered, they're stacked on top of another. And all of them, because they operate on this homogeneous language, have very simple interfaces. The interfacing problem is much simpler because all you need in between is an interface that speaks bit strings. As long as you do that, anything can be swapped and rearranged, recombined, reconfigured in any way you want, so that content can run on a different service. So you build an app and it runs both on the App Store and the Android Store, and it runs on your tablet, your laptop, or your phone through 3G, 5G, 2G, wireless, or Bluetooth. Yeah. So all these things are layered, modular, and entirely loosely coupled. That is unique here in digital technology, and an extension of the modular architecture from products that we've seen for a longer time, such as Dell computers, IKEA furniture, or bicycle or cars, for that matters. Yeah. So what that means is that every component in itself is basically agnostic from anything around it, as long as it has this interface that speaks homogeneous bit string language. So whatever comes in the form of bit string information. Whatever goes out is again in the form of bit string information. Yeah, so that means the different layers can be combined, patched, loosely coupled in the design of the product. Yeah, so as we're building the offering, but also in whatever people do with it. Yeah, so with the phone, I can do whatever I want, and I can add things whatever I want, as long as I make use of the interfaces that it has. Yeah. So whatever I'm changing in any one of these modules, in any one of these layers, in theory, doesn't affect changes on the other layers, as long as I keep it contained within that module and don't affect the interfaces to the other modules. So again, here a classic example, I mentioned this earlier. Dell computers were basically one of the first companies that built technology products, computers, and they started modularizing and said, well, we basically give you a configuration option of you select any component you want for GPU, for processor, for hard drive, for disk drive, for screen, and they'll just rearrange everything together on the basis of standardized interfaces between the different components. So why is this important? Because this affects lots of things. Number one, in how the products or offerings of a company are actually being built, and of course, how you can use them. Yeah. So digitization means that we change products that were either integral or modular to have a layered modular architecture, meaning that the different components on the different layers can be recombined and only loosely coupled, which fosters something that's called generativity. Innovations can spring up at any layer of any object and can, during design and use, and they can change whatever that thing is capable to do, and it becomes innovative in this sense, because there's a new possibility of doing different and new things all the time, as long as your product features technology components that are layered or modular. The second aspect that we need to talk about is this notion of addressability. So we already mentioned that technologies come with interfaces that allow them to be identified and addressed. Yeah, some way of feeding bitstring information in or accessing bitstring information out of a module, a component, a technology, or a product. So there's different types of these interfaces. So some of the more well-known ones are what's called APIs, application program interface. They operate on the software layer, but you can even think about physical interfaces such as a USB cable, what do they call, the FireWire cable, and so forth. So, and even these are becoming more and more standardized. For example, what you see here is a USB-C cable, which is now in Europe anyway, from next year on, I believe, or from this year on, is now the standard interface for any computing device. So that there's one way of even physically making technology or different components or different product accessible, always through the same cable. Or, of course, if they have wireless connectivity, you can connect them without a cable, of course. What does that mean? That means that technologies are, by definition, interoperable. They can always work, in principle, with other product systems, offerings, components that also leverage digital technology. It also means that no piece of technology ever exists in a vacuum. It always exists as part of a much broader ecosystem. Yeah, think of it. The phone, your smartphone will not work without a 5G network around it, or it won't work without wireless. It becomes very meaningless. The content of an app wouldn't work without a phone. Yeah, so we need, for example, both 5G network throughout the city, and people having, computing capable devices in their pockets, mobile computing, watches, phones, or tablets, for an app for Uber to even work. And if you have a car sharing app such as Drive Now or BlaBlaCar, you would even have to have the car to be accessible, because otherwise the app wouldn't be able to open the door for you. So this notion of addressability also fosters generativity. So the modularity fosters generativity, but the addressability also, because it allows even third parties, so parties outside of the originating firm, to also join the recombinant information process. And the classic example here is, of course, the App Store or its equivalent on Google phones, Android phones, and so forth. So, which is really an interface that they created for third parties, for other companies, even competitors, to also provide new modules, usually content modules, that would work on your device, on the service layers, in the network layers, whatever you're using, whether it be an Android phone on a 5G or an Apple phone in a wireless situation, or a Microsoft laptop operating through Bluetooth. It doesn't matter. It now provides this possibility through addressability. One maybe less obvious example of this, where it's not just firms purportedly through contractual arrangements offer official versions of new components that you can download onto another piece of technology like a phone. A less obvious example is hacking. So for example, the Thermomix is a piece of digital technology product. It is a cooking pot, with blade in a pot, and it can heat up and so forth. But it's also connected to this platform called CookieDo. It has connectivity, it's addressable, it is modular because you can update the software without changing the hardware and so forth. And through the CookieDo platform, for example, you can access the machine, of course. And the intended way, of course, is that you have this CookieDo platform, which is basically a recipe community platform where people can create, upload, share, and download recipes with cooking instruction onto their machine, and then literally start cooking the physical product. But of course, it also allows you to hack the machine. Hacking is a term that says that you can reconfigure and change the behavior of the machine, maybe in unintended ways, or let's say at least in ways that the original design of the machine wasn't intended for. That's called hacking. And for example, there are Instagram and YouTube social media influencer accounts who made a career out of hacking things like the Thermomix by using the software platforms to address and connect to the machine, and changing the configuration machine so it literally behaves differently and cooks differently and so forth. So this notion of addressability is not only changing the fundamental nature of the products, but it also is key to the emergence of what is now known as ecosystems. So large, interconnected industrial settings or markets where many, many different companies with some of their products or offerings and technologies are all interconnected and to provide some value or with each other, to each other, or to a customers. So this, for example, is a fintech ecosystem where you see that many, many different companies that specialize in some aspects, say in remittance, wealth management, loan management, investments, payments, and so forth, together through, for example, a core banking platform that has an API and interface layer that can be addressed by all these other players, and together they provide more and more value through the banking platform, through the different components that they add and address. The next notion we want to look at is agency. So the ability for digital technologies to act in their own rights with little to no human intervention. On the right-hand side, you see a classical, a very vivid example of technology agency for robots. So this is a company, Boston Dynamics, a startup that has become very popular because it creates humanoid robots, but also robots that are, like animals. Like on the left-hand side, you see the robo dog, which you can pet, which reacts, which can jump, fetch ball and do all sorts of doggy things, which are obvious examples where you have physical machines that act, in this case, like a living being. And of course, some of these are not necessarily new. So this is a very classic robot featuring in a car manufacturing plant. So we've had these types of agents or technology agents for a long time that were acting autonomously, but in this particular example, in a very deterministic way. So the machines could do one thing or two things in a deterministic sequence, so that they actually required all the inputs and outputs to be arriving at a particular point in time, particular shape, particular sequence, particular timing, and so forth, for them to do whatever they're meant to do. So this is an example of a robot that literally replaced a human and consistently always operates this, performs the same function, of course. But digital technology agency is different from these classical form of agentic technologies. Yeah, so these traditional autonomous tools, like the robot in the car manufacturing plant, were deterministic, as I said, and still human bracketed. So human meaning that human still decided what they were doing, when they were doing it, on what object we were doing it, what the output was, and so forth. So you literally had to program that into the machine to operate in a particular way. You could turn it on and off with a switch and so forth. Digital technologies agency is different. It is probabilistic and actually autonomous. So without human bracketing, without any human intervention or oversight. So ChatGPT is a very good example for such a probabilistic and autonomous tools. This is a tool that you can talk to, and it generates outputs. You know, most notably text, but it can also generate other outputs like, you know, tables or data or whatever else. But it's probabilistic. You don't know what it's doing, and it does that autonomously. Like there's no human overseeing it or controlling it in the background. It really acts in its own right on its own. On the left-hand side, you see an example from Tallinn in Estonia, where they have autonomous vehicles that are technologies for last mile delivery. So for a very famous logistic problems in products, namely, how do I get that last mile from the bakery store to the customer? You know, like where you usually have a food delivery platform, say, like Deliveroo or Gorillas or anything like this. They've invented technologies which are not self-driving cars, but rather self-driving robots that are at walking speed and can independently roam through a city on the footpath, not on the road, very importantly, and deliver products. You can open them up, and it has basically like a hatch, and you can put stuff in there. And that could be your Coca-Cola, it could be McDonald's delivery, or, you know, bread rolls or whatever, and deliver it to your doorstep and communicate with you. And they are completely autonomous. They are very secure. They're very safe. And they're literally roaming the city. If you ever come to Tallinn, you will see them wandering around the street and behaving much better, to be honest, and much more consistently than humans would in foot traffic. So this agency here, again, probabilistic and autonomous, which is different from agentic technologies of the past. The next aspect we look at is the notion of reprogrammability. So what is here in academic terms, we would call it the malleability of form and function. So the ability of technology to evolve and change and be changed. Yeah. A traditional example from the 90s were universally programmable remote controls. Sort of the idea that as people had more and more, you know, media devices, they all had remote controls. You ended up with 6-7 remote controls, and then there was a market for these universal programmable controls where you could teach them to perform the function and the wavelengths and the signal length of the different, you know, remote controls you had, from your Samsung television to your Panasonic hi-fi system or whatever else, and program this way. They were also reprogrammable in a sense, in a very basic format. Yeah. Digital technology has a very heightened, high ability to be reprogrammable because of, again, of this bit string format, because they're essentially ephemeral electric current, right? The electricity is flowing or not. And importantly, the format of that language, of this information that we're processing, is syntactic. It has a grammar, but it's not semantic. It doesn't have predefined meaning. It can mean whatever we want the sequence of zeros and ones to be. So that means we can change the content as well as the behavior. You know, we can change what technology do with inputs that arrives in zeros and ones. If we tell them this is a number, please calculate something, or it's a text, please, you know, create a new sentence with this text. we can change that because they're effectively all zeros and ones that are either flowing as electric current or not. This is important because this also allows not just to change what a system or a technology or product is as we design it, but we can even do so after we've launched it and sold it to the customer. So no longer is our ability to change, interfere or, reprogram a product, left while we have it as the firm, while it's in our, vicinity and our access. We can even do so after we've literally sold it over the counter to customers. And one very good example of that is how that changes, post-product launch operations, such as a recall service that we would have in car manufacturers, which is a very expensive and unwanted operation, namely when you figure out that there's an issue with your car after you've sold it to the customers, and that the issue is so severe that you literally have to get all the cars back and change the issue. So for example, the braking system is deficient, or the transmission system is dangerous to, health or whatever else, that you literally would have to bring the cars back into your garage, recall them, bring them back so you can fix that. Of course, this also happens with cars that have digital technology in them. So for example, Tesla also has similar issues every now and then, and they also have to issue a recall at some stage. The key difference is, of course, is that they don't physically have to bring back the vehicles. The vehicles have digital technology components in them. Technology is addressable and it's reprogrammable, meaning that whatever the issue is, they can fix that over the air. They can fix that digitally by changing how it processes zeros and ones, but they're changing, literally the operating system of the car. It also leads to other types of things, not just to recall operations, but it also leads to phenomena such as templating. Templating is the idea that you take a product that exists as a digital technology, and you can copy that and slightly modify it to create a different product. So Uber is a nice example for this templating. So you have the Uber service, which is a ride-sharing service, but it also serves as a template for example, not ride-sharing between passengers, but between objects, maybe food. So it's the same thing, essentially, but instead of people being driven around, it's food being driven around. That gives us Uber Eats. And it's basically a copy with a slight adaptation to it, because the technology itself, the product is malleable, right? It's pre-programmable. Or you can reprogram it slightly that you have UberX, which is the cheap version of Uber, where you get less luxurious cars that are being driven around in, but you can save a little bit of money. So this is basically templating, creating variants of products at very marginal costs, close to none. There's some costs involved in core, of course, and allow you to even produce different types of offerings on the basis of one template offering. And finally, the fifth emerging capability is datafication. Datafication, as I've explained, it means that technologies both use and generate digital traces when they're being used. Yeah, digital traces are any activity or events that are stored and logged digitally. Yeah, these are your cookies on your internet browsers. These are the click streams as you use an input device. This could be user-generated content or other types of content that appears on any of your devices, any of your apps, or anywhere else. They come from user interaction, machine states, executed functions, human or machine input, anything like that. And this data in itself, of course, becomes then also available to whoever has access to this data to inform further innovation. Yeah, and this generates a number of really key, important managerial effects, and the most prominent of which is called the data network effects. Data network effects are not a new thing in themselves. Network effect is a term that describes a situation where the value of an offering increases the more users participate. Yeah, so a classic example of a technology product that has that is a telephone. If I'm the only person on the planet that has a telephone, it's of limited value. If I have another person, that is valuable to both of us. And the more people join this telephone network, the more valuable it becomes to everyone involved, because the more people we can talk to and contact, the better is it for everyone. So that is a classic network effect, and it doesn't hinge on data. And per se, data in itself is also not necessarily inherently valuable. Data is a byproduct or a condition for some products to function. It's a byproduct of digital technology products that they generate this. So, and most data doesn't produce a real network effect, and most data network effects, even if they exist, aren't even that powerful. But if companies find a way of creating and leveraging data network effects, then they have a phenomenon of exponential value growth that is very prominent, right? So a data network exists when a technology's value growth of the result of more usage via the accretion of data. So one example where that is very evident is, again, Uber. What Uber does is, as soon as it has users using its technology for ride sharing, they create data, right? The rides, the requests, how long it took, how much money they paid, what rating they gave to the driver, and so forth. All this data, they actually feed into an analytics algorithms. Yeah, they analyze this data to understand better how people are using Uber for ride sharing, which rides are more economically viable, which drivers are more popular, why that might be, which of them are more on time, less on time, and so forth. All this data, Uber found a way of analyzing it and using it to improving all the algorithms that are part of the product, the matching algorithms, the route planning algorithms, the rating algorithms, and so forth. In so doing, the service itself gets better and becomes more valuable to users, which leads to more users jumping on the platform and joining the fun, which then again creates more data that can be used. So this becomes a reinforcing circle that describes this data network effect that is possible. Datafication not only creates this data network effect that hinges on your firm actually exploiting this data. So you do have to put in a capability to analyze and to make the product itself better. Yeah, and Uber is famous because they did both of these things autonomously, automatically through an algorithm for learning, an algorithm for self-improvement as well. And another thing that you can do, of course, from datafication of your product is that you can learn a lot about the product in use, which you can then use to innovate the product further. And a nice example of one that we studied at some stage is from the video game industry by a company called Ubisoft, which is a leading video game publisher. And the case that we looked at is one particular title, Ghost Recon Wildlands, which is a very, very famous product, a video game, and had lots of users, so 7 million users. And what is unique about this particular game is that it maintained a very long history of people playing that game. Now, that is maybe unique, but you have to think of it as like a movie. When lots of people want to watch a movie, but as soon as they've watched it, you've kind of seen it. And then it drops in the value that it generates for a firm very quickly, right? So the biggest margin for Hollywood movies are the first 2 weekends, and then it sort of declines. It's not dissimilar to video games, and that's a big issue because video games are very expensive to produce. They cost hundreds of millions of dollars to produce, and you obviously want to, once produced, because it took a long time and a lot of money to produce these things, you wanted to generate and capture value as long as possible. Yeah, so it was a very big success for a long time, built by 3,000 contributors, but they also managed to keep the product, keep the game being played by its users for a very, very unusually long time, for years to come. What did they do? What they did is they did continuous product innovation. They continued to innovate their product even after the launch, which is possible because it was an entirely digital product, right? So it was reprogrammable, it was addressable. They could literally update and change the game over time as after they've already sold it, but it was not anymore a box with a CD-ROM in it. It was just a title that people could download. Yeah, for the reasons we already discussed. Moreover, they engaged in, they leveraged this datafication. So as people were playing the game, because it's a digital product, they left all these footprints, all this data about what people were doing in the game, and they built a capability to use this data to figure out how they should innovate it. They did it in 3 ways. The first one is data-driven exploration. That meant they found a way to analyze the playing data from the players to explore new patterns, anomalies, and just see what people were doing, and then generate innovations that would speak to this particular audience. For example, one of the things they noticed is that some people in this game were not actually playing the game. They weren't doing any missions. They weren't shooting others. They weren't doing, they weren't doing what everybody else is doing. And they were doing something really weird, differently. So the algorithm picked up on this because they saw some behavior in the game data that was unusual to what everybody else is doing. When they identified it, is that they realized that some players go into this particular game, which is a war game where you run around and shoot other people, and they didn't play this game. They didn't play any of the missions. They didn't do any battles. They reenacted scenes from the Second World War, for example, because the game is fairly photorealistic in that sense. And they weren't even playing it; they were just using it basically as a role-playing game, so to speak. What they then decided is to create a heat map, which allowed people to identify whether other types of role-playing people were also on the map, so to speak, in the game, that they could latch up to and sort of, co-enact their role-playing while not being bothered by all the shooting that everybody else was doing. A second example is what's called data augmented ideation. In this example, what they did is they innovated the product, changed the product after it's being shipped, by combining human expertise, creativity with data insights they got from in-game playing data. One example for that is that in these games, a key issue is that you maintain a good balance between the two attacking parties. Like one party is the Russians and the other party is the Americans, and they fight each other, and it should be balanced. Shouldn't be favor each of one of the two sides. That's difficult to foresee, but of course that emerges very quickly once you start seeing what people were doing. So what they've done is they noticed from the playing data imbalances like win rates, death, and all these sorts of things, and then they used this data to create, through human expertise, create changes to the actual maps, to what, for example, different locations on the map would look like, and thereby together augmented digital data and with human ideas created updates and changed the maps so that the playing field was always level. And a third example of how they use data is basically the run and run. So the first one was data driven, then to a human designer. The second was basically augmentation, like both together jointly. And the third one was that they had human designer teams come up with new ideas for new missions, for new objects like weapons or armory or whatever else. And then they use data to validate these design ideas and test it before going live, so to speak. Yeah. So one example for that is when they started introducing a credit economy. Yeah. So sort of things you can buy with in-game, not with money, real money, but with sort of their own little, fake money inside the system. Yeah, credit economy and prestige economy, where you can buy really cool gear that no one else would have and stuff like that. So this brings us to the end of showing what is different about digital technologies. And what is different is that they come with new emerging capabilities that separate what these technologies and they use in digital, in products and offerings of a firm can achieve. And because this is possible, the role of technology in itself changes from being no longer in the back office on a computer screen, but literally front and center in the products and offerings of a firm themselves. And to summarize all this, I give you one case study if you want, namely the role of technologies in retail and how these 5 different capabilities play out. Modularity, you can see, for example, if you look at cashier systems, that you can, that basically have the different functionalities like categories of products and so forth. And you can now transport and port onto different types of devices. Yeah, so for example, you have a cash system as a cash out fund. You can have that as a tablet, as a Shopify software solution that runs on different devices. And in some stores, you can self-checkout because they basically provide the same functionality as an app that you can download on your phone. You can do yourself, right? For example, in some Edeka stores in Nordstadt, in Hamburg, they now have a self-checkout functionality without these terminals, but actually, as you go out through the store, your smartphone can do that for you. Addressability, you can see in the products themselves. the items that are on the stores now having digital product codes that are actually digital readable, no longer just like little paper-based pricing information, but actually digital price tags that you can scan with a scanner, but also increasingly with your smartphone itself, and then therefore make it addressable by other types of technologies, importantly, especially technologies that the consumers would have themselves. Agency, you can see in how they have marketing campaigns, from brochures that were printed to now basically autonomously optimized and individualized offers and advertisements that are different for every person, and that are not created by a design team or by a marketing team, but rather that algorithmically, autonomously, and probabilistically create individualized shopping offers for every single person based on an algorithm that feeds on your personal shopping style and behaviors and interests and so forth. Reprogrammability you see in these price tags again, that since we make them digitally readable, you can also, of course, change the prices, right? That leads to this idea of dynamic pricing, that in principle, at any time for any one person, you can offer a different price, much like you would see in airline tickets, for example. In datafication, you can see, for example, that as you do this, you gain more and more insights into what is going on in the stores. So, for example, stores offer free Wi-Fi as a service to customers, sure, but also that this way they can actually see better trace data of where you are and how you move between the aisles in the store. So your movement patterns become a piece of data that they can use to innovate and rearrange the aisle sequences, what is placed where, and even understand better which product at which point in time for which customers it should, for example, move to the front of an aisle or to the back of an aisle, etc., and so forth. So these would be 5 examples for these 5 capabilities as they're being used in retail. And that brings us to the end of this video lecture. Thanks for watching, and thanks for listening.